Point set registration, a fundamental problem in computer vision and machine learning, involves aligning two sets of points in a way that preserves their topological structure. The kNN-Res method, a residual neural network-based approach, addresses this challenge by leveraging a global smoothness constraint to preserve local topology. This differs from coherent point drift, CPD, which relies on a local regularization term. The kNN-Res method's flexibility makes it well suited for registering multiple objects and articulating pose changes. A Jacobian-based cost function and geometric-aware statistical distances are employed to tackle issues related to local rigidity and global non-rigidity. The preservation of the k-nearest neighbor (kNN-Graph) of the target data is justified through the use of the Jacobian cost. To efficiently handle high-dimensional point sets, a constant time stochastic approximation of the Jacobian cost is introduced. The effectiveness of kNN-Res is demonstrated through two-dimensional toy examples and high-dimensional flow cytometry datasets, where the goal is to align two distributions of cells. Notably, kNN-Res outperforms existing methods like CPD in terms of flexibility and efficiency, making it a promising approach for point set registration tasks. By preserving the topological structure of the target point set, kNN-Res provides a more accurate and robust solution for a range of applications. In computer vision and bioinformatics, point set registration is a fundamental problem that involves aligning a deformed target set of points to a reference point set by applying a constrained transformation. This alignment enables improved comparison and analysis of the two sets of points, with applications in object tracking, body shape modeling, human pose estimation, and removal of batch effects in biological data. Point set registration techniques are categorized based on two main properties: correspondence-based versus correspondence-free, and rigid versus non-rigid transformations. Rigid registration techniques, which assume preservation of pairwise distance between points, are simpler and modeled as a combination of rotation and translation. In contrast, non-rigid transformations allow for more flexibility but introduce an infinite number of possible transformations, making the problem ill-posed. To address this, non-rigid registration techniques employ additional constraints. The alignment problem can be formulated as finding a map that transforms data points sampled from an underlying distribution Q to distribution P, preserving the topological structure of data sampled from Q. This is an ill-posed density estimation problem, requiring an additional desideratum for the map to be as simple as possible. A map is considered simple if it is close to the identity transformation, visualized as data points sampled from Q moving along a regularized displacement vector field F. The proposed approach, kNN-Res, is designed to preserve the k-nearest neighbors (kNN-Graph) of the transformed data points while maintaining the biological signal of the transformed data. This approach is implemented and available under the MIT license. The problem of aligning two point sets, a reference point set R and a target point set T, is formulated. R and T are generated by probability distributions P and Q, respectively. A k-nearest neighbor, kNN-Graph, is associated with the target point set T, which must be preserved after transformation. The kNN-Graph is a directed graph where an edge exists from node I to j if and only if yj is among Y's k most similar items in T under some similarity measure ρ. The goal of an alignment method is to find a transformation phi parameterized by theta such that the statistical distance d between the transformed target points phi, y, theta, and the reference points x is minimized, subject to the constraint that the kNN-Graph of the transformed target points is preserved. Existing approaches, such as coherent point drift, CPD, use a Gaussian mixture model to induce a displacement field from the target to source points and employ local motion coherence to constrain the field. However, CPD has limitations, including global smoothing constraints that make it locally inflexible, rendering it unsuitable for articulated deformations in 3D human data, scenes with multiple objects, and biological data. This work introduces a Jacobian orthogonality loss as a sufficient condition for preserving the kNN-Graph of the data. The Jacobian orthogonality loss is defined as Jx minus ID, where Jx is the Jacobian matrix at a point x and ID is the d times d identity matrix. This penalty has been proposed in other contexts, such as unsupervised disentanglement and medical image registration. Previous approaches have employed finite difference methods to compute the Jacobian penalty for BSP lines warping transformations, but these methods are limited to low dimensions due to the nature of the transformations used and the way the Jacobian penalty is computed. The authors address the limitations of existing point cloud alignment methods by introducing several key contributions. They employ Hutchinson's estimator for efficient computation of the Jacobian loss in high-dimensional point clouds, a scalable ResNet architecture as the warping transformation, and geometry-aware statistical distances. The choice of ResNet with an identity block is well suited due to its ability to learn identity mapping easily, aligning with viewing alignment similar to CPD as a regularized movement of data points along a displacement vector field. They also discuss the moment-matching ResNet, kNN-Res, which utilizes a similar ResNet architecture with RBF kernel maximum mean discrepancy as its similarity measure. However, the authors highlight that kNN-Res lacks topological constraints to preserve the topological structure of the transformed data and limit the nature of the learned transformation, as demonstrated in Figure 1. To overcome these limitations, the authors incorporate synchrone divergence into their framework, providing a more comprehensive approach to point cloud alignment. This approach ensures that the topological structure of the data is preserved while allowing for flexible transformations, thereby enhancing the accuracy and efficiency of point cloud alignment. Maximum mean discrepancy, MMD, is a measure of the difference between two probability distributions, defined as the integral of the squared difference between the kernel functions of the two distributions. Typically, a radial basis function, RBF, kernel is used, which is suitable for high-dimensional Euclidean feature spaces and has low training complexity. However, RBF kernels have limitations, including blinding the model to details smaller than its standard deviation and causing the vanishing gradient problem. To address these limitations, optimal transport, OT, losses are considered, which produce more stable gradients but require solving computationally costly linear programs. An efficient approximation of OT is entropic regularized OT, defined as the minimum cost of transporting one distribution to another, regularized by the Kullback-Leibler (KL) divergence. This problem can be efficiently solved using the synchrone algorithm. The synchrone divergence combines the advantages of MMD and OT, defined as the entropic regularized OT minus the average of the entropic regularized OT between each distribution and itself. The synchrone divergence converges to the standard OT as the regularization parameter approaches 0 into half the squared MMD minus the kernel-based cost function as the regularization parameter approaches infinity. In the context of point cloud registration, other related approaches include thin plate spline functions-based techniques, which preserve local topology via local rigidity on the surface of a deformed shape. However, these approaches are not scalable. In contrast, the synchrone divergence provides a scalable and efficient solution for measuring the difference between two probability distributions, making it a valuable tool for applications such as point cloud registration. Point cloud registration methods, traditionally limited to three-dimensional point clouds, have been enhanced by incorporating deep learning paradigms to address scalability issues. These approaches can be categorized into two types: features-based and end-to-end learning. Features-based methods employ neural networks for feature extraction, aiming to estimate robust correspondences through sophisticated network architectures or loss functions. In contrast, end-to-end learning methods combine multiple steps into a single objective, solving the registration problem directly by converting it to a regression problem. Graph matching techniques, another class of methods, formulate the registration problem as a quadratic assignment problem, QAP. However, these methods face the challenge of finding efficient approximate solutions to the NFARD QAP. Techniques such as congruent sets Gaussian mixture, CSGM, high-order graph, and factorized graph matching, FGM, have been developed to address this issue. The proposed model parametrizes the transformation phi as a residual neural network and formulates the optimization problem as a combination of alignment loss L1 and topology preserving loss L2, weighted by hyperparameter lambda. The alignment loss measures the distance between the transformed point cloud and the target point cloud, while the topology preserving loss ensures the preservation of the nearest neighbors, kNN-Graph of the data. This is achieved by enforcing the orthogonality of the Jacobian matrix, which is proven to be a sufficient condition for preserving the kNN-Graph. Two statistical distances, Sinkhorn divergences and maximum mean discrepancy, are employed to measure the distance between the point clouds. Sinkhorn divergences provide a computationally efficient approximation of the Wasserstein distance in high dimensions, converging to the maximum mean discrepancy. Researchers have developed a novel neural network architecture for aligning two different distributions, leveraging optimal transport theory and maximum mean discrepancy, MMD. The architecture introduces a new cost function, S, alpha, beta, which combines optimal transport with L2 norm cost in MMD. This cost function can be efficiently computed using samples from the reference and target distributions. The proposed architecture utilizes a simple res-net identity block as the transformation function, where the output dimension is equal to the input dimension. The transformation function is calculated as phi, y, theta, equals y plus delta, y, theta, where delta, y, theta, is a standard multilayer perceptron, MLP, with leaky ReLU activation functions, and theta represents the trainable weights of the network. This choice of architecture ensures that the alignment function can be viewed as a smooth displacement field, following the recipe from the Continuous Projective Dictionary, CPD, method. Preserving the nearest neighbors, kNN-Graph of data points is crucial in the transformation process. A vector-valued function f r⁻n right-pointing arrow r⁻n preserves the kNN-Graph if, for every 2 points v and w in some small epsilon neighborhood of U, the following condition holds: uv_2 to the power of 2 less than uw_2 to the power of 2 right-pointing arrow f u f v_2 to the power of 2 less than f u f w_2 to the power of 2. This condition ensures that the transformation maintains the local structure of the data points, which is essential for maintaining the integrity of the data during alignment. The proposed approach offers a novel solution for aligning distributions using optimal transport and MMD, along with a specifically designed neural network architecture that preserves the kNN-Graph of data points. The orth_Jacobian_FINDIF function computes the Jacobian deviation from orthogonality at data points z using a finite difference method. This PyTorch algorithm takes a function g, input z as a batch of data points, and an optional epsilon value for the finite difference approximation as inputs. It outputs the mean of the absolute difference between the squared Jacobian and the identity matrix, indicating the Jacobian's orthogonality. The algorithm first computes the function g on the input z and creates an identity matrix I. Then, it perturbs each dimension of z by adding epsilon times the identity matrix to create a new set of points zdz. The Jacobian matrix is approximated using finite differences, and the squared Euclidean distance between the Jacobian and the identity matrix is calculated. Finally, the mean of this distance is returned as the Jacobian penalty. The mathematical derivation underlying this approach begins by linearizing the vector field f around a point U using the Jacobian matrix J. It then computes the squared distance between 2 points U and V in the input space and their corresponding outputs in the function space. Assuming the Jacobian matrix's orthogonality, the squared distance in the output space equals the squared distance in the input space, illustrating the preservation of distances under an orthogonal transformation. Computing the Jacobian matrix for a given function f is crucial. While analytical computation via autodifferentiation modules is possible, it is highly inefficient. Therefore, a numerical approximation via finite differences is employed, as demonstrated in algorithm 1. This approach enables efficient computation of the Jacobian penalty, essential for evaluating the orthogonality of the Jacobian matrix at various data points. The computation of the Jacobian matrix is a crucial step in training a model, particularly in ensuring orthogonality. Given a d-dimensional vector x, the partial first derivative of f with respect to xi is defined as partial differential f partial differential xi equals lim e right pointing arrow 0, f, x plus ea, f, x, e, where a is a standard basis vector. The Jacobian matrix Jx is composed of these partial derivatives. To ensure orthogonality of the Jacobian at x, the loss L2 is minimized, defined as L2 equals 1 per meter n area summation x element of x, jxid, where m is the number of points in x. The training process involves two sets of d-dimensional vectors, a reference point set R and a target point set T. The model is trained by sampling points from R and T, creating matrices X and Y, and feeding Y to the model to obtain Y. The GMM posterior probability is computed as a similarity matrix, and the loss L1 is estimated as the negative log likelihood. The Sinkhorn divergence approach is also used to compute equation 10. The soft kNN operator is applied to construct the kNN-Graph for both the input Y and the output Y, and the loss L2 is computed as the mean squared error between the two. To efficiently compute the Jacobian for low-dimensional point clouds, a stochastic approximation of the orthogonal Jacobian loss is introduced. Given a vector-valued function f and a sample x, the loss Lj, f, is defined as Lj, f, equals jj hollow bullet, 1I, 2. The Hutchinson's estimator of Lj, f, is approximated as Lj, f, equals var, re, jj, re, equals var, junior e, where re is a scaled Rademacher vector. This approach is efficient and has a constant computational cost, making it suitable for high-dimensional data. The algorithm for training the model involves sampling points from the reference and target point sets, creating matrices X and Y, and feeding Y to the model to obtain Y. The losses L1 and L2 are computed, and the total loss L is minimized using backpropagation until convergence. The stochastic approximation of the orthogonal Jacobian loss is used to efficiently compute the Jacobian matrix, ensuring orthogonality. The use of the Hutchinson's estimator and the stochastic approximation of the orthogonal Jacobian loss are novel ideas in this paper, providing an efficient approach for high-dimensional data. Ensuring the orthogonality of the Jacobian matrix is essential for many applications in machine learning and computer vision. The kNN-ResNet model's training procedure is presented in algorithm 2, which takes as input point sets R and T, blurring factor sigma, step size E, regularization parameter lambda, and batch size B. The algorithm iterates over many batches of size B from R and T until convergence, computing the loss function L at each iteration. L consists of two terms, L1, which measures the similarity between the transformed point sets X and phi, Y, using either Sinkhorn divergence or maximum mean discrepancy, MMD, and L2, a penalty term enforcing orthogonality of the Jacobian matrix J. The Jacobian matrix J is approximated using a finite difference method, computed as the difference quotient of the transformed point sets. The loss function L is then minimized using backpropagation. Although this approach does not guarantee orthonormality, it produces comparable results to the standard finite difference method and can be efficiently implemented in PyTorch. The proposed model has three main hyperparameters, sigma, E, and lambda. The blurring factor sigma controls the trade-off between optimal transport, OT, and MMD, with smaller values resulting in an exact OT solution but slower convergence. The step size E controls the radius of topology preservation around each point, with larger values producing globally isomorphic transformations. The regularization parameter lambda prioritizes regularization over alignment and is typically set to a small value. An additional hyperparameter k is introduced when using a stochastic approximation of Jacobian orthogonality for high-dimensional data, determining the number of Rademacher vectors sampled to estimate the Jacobian orthogonality penalty. A larger value of k tends to produce a more accurate estimation, but k equals 5 is found to be sufficient for the experimented datasets. The choice of hyperparameters is crucial for the model's performance. Default values are set to sigma equals 0.01 for datasets in the first quadrant of the unit hypercube, with E chosen based on the desired level of topology preservation and lambda set to a small value. The value of k is chosen based on the dimensionality of the data and the desired level of accuracy. Implementing the Hutchinson approximation of the Jacobian off-diagonal elements is crucial for efficient point set registration. A novel PyTorch algorithm, stochastic_Korth_Jacobian, is proposed to address this challenge. This algorithm takes as input a function g computing the Jacobian penalty, a batch of input data points z, the number of directions to sample k, and an epsilon value for the approximation. The output is the mean of the absolute difference between the transposed Jacobian matrix multiplied by itself and the identity matrix, which measures alignment error. The algorithm's performance is evaluated on several datasets, including the Cui-Rengarajan synthesized dataset and single-cell RNA data. For 2D data, the root mean squared error, RMSE, is used to assess the proposed model's performance and compare it with state-of-the-art models like kNN-Res, MM-Res, CPD, TRS-RPM, RPM-LNS, and GMMREG. The results demonstrate the proposed model's effectiveness in aligning point sets under various deformation levels and sample sizes. The Hutchinson approximation is essential for efficiently computing the Jacobian matrix, which is critical for optimizing point set alignment. The stochastic approximation method employed in this algorithm enables efficient computation of Jacobian off-diagonal elements, making it suitable for large-scale datasets where exact computation is computationally expensive. Experimental results highlight the proposed model's robustness and efficiency in handling different types of deformations and sample sizes. Comparisons with other models emphasize the strengths of the proposed approach in achieving better alignment accuracy, particularly at higher deformation levels. The proposed algorithm contributes to the development of more efficient and accurate methods for aligning point sets under various conditions. Figure 2 illustrates the Chinese character deformation example, showcasing the original and deformed sets, vector field, and final alignment. In this example, the author's kNN-Res approach outperforms MM-Res in handling non-rigid deformations, successfully converging with a set of hyperparameters E equals 0.005, lambda equals 10 to the power of 5, sigma equals 0.001, and 50 hidden units. The Atom optimizer is used with a reducon plateau scheduler, starting with a learning rate of 0.01 and reducing it by a factor of 0.7 to a minimum of 5 times 10 to the power of 5. Visually, the estimated transformations from kNN-Res appear simple and coherent. To quantify neighborhood preservation, the authors employ the Hammill loss LH, which measures the difference between the kNN-Graph before and after transformation. The formula for LH is given as LH equals n-ary summation, I equals 0 to mix, n-ary summation, j equals 0 to mix, I, pk, I. J does not equal pk, I, j, where pk, I, j is the I, j element of the kNN-Graph matrix before transformation, pk, I, j is the corresponding element after transformation, and I is the indicator function. Figures 5b and 5a demonstrate the difference in neighborhood preservation between MM-Res and kNN-Res for the Chinese character and fish datasets, respectively, under 3 levels of deformations. Notably, kNN-Res generally incurs smaller alignment errors and converges under large deformation levels, despite the added topology regularization term. The authors then apply their approach to high-dimensional CYTOF data, which is prone to the batch effect problem. This problem arises from systematic non-biological variations during data acquisition, leading to inconsistencies across different batches. Figure 3 showcases the fish deformation example, highlighting the original and deformed sets, vector field, and final alignment for both the Chinese character and fish datasets. The evaluation metrics employed in the study are presented in Figure 4. Batch effects, which occur when the measurement process introduces a distributional shift in similar samples, pose a significant challenge. This phenomenon compromises the intracomparability of samples, a crucial aspect in downstream tasks such as disease diagnosis. Human experts typically intervene to remove these batch effects. The CYTOF dataset, curated by the Yale New Haven Hospital, consists of 2 patients with 2 conditions measured on 2 different days. Each of the 8 samples has 25 markers, representing separate dimensions, including CD 45 feet, CD 19 feet, and CD 127 feet, among others. The number of cells per sample ranges from 1,800 to 5,000. The samples are split, with those collected on day 1 serving as the target and those collected on day 2 serving as the source. This setup enables the investigation of batch effects on the alignment of high-dimensional single-cell data. The evaluation metrics in Figure 4 will assess the performance of the proposed method in addressing batch effects. These metrics will provide insight into the method's ability to mitigate the impact of batch effects on the alignment of high-dimensional single-cell data. The proposed method aims to reduce the distributional shift introduced by batch effects, thereby improving the intercomparability of samples and facilitating more accurate downstream analysis. The authors present an empirical evaluation of their proposed method for aligning distributions of shapes with varying levels of deformations. In Figure 5, the Hamming loss metric is illustrated for 3 levels of deformations, showcasing the performance of their approach. The figure demonstrates the impact of increasing deformation levels on the alignment of distributions, with level 1 exhibiting the least deformation and level 3 showcasing the most severe deformation. To further investigate the effect of incorporating geometric constraints on the alignment process, the authors visualize the principal components of the reference and target samples in Figure 6. Blue and red dots represent the first and second principal components, respectively. This visualization highlights the importance of incorporating geometric constraints, as evident from the improved alignment of the principal components when lambda is set to 1.0. The unaligned distributions, shown in Figure 6a, exhibit significant discrepancies between the reference and target samples. In contrast, the aligned distributions without geometric constraints, depicted in Figure 6b, demonstrate some degree of alignment, although with noticeable deviations. The incorporation of geometric constraints, as shown in Figure 6c, yields a more accurate alignment of the distributions, underscoring the significance of this approach in shape analysis tasks. The mathematical formulation underlying this approach is rooted in the concept of optimal transport, which seeks to find a probabilistic coupling between the reference and target distributions that minimizes the transportation cost. The inclusion of geometric constraints is achieved through the introduction of a regularization term in the optimization problem, which penalizes deviations from the desired geometric structure. This page builds upon the previous sections, which introduced the problem formulation and the proposed methodology. The empirical results presented here provide evidence for the efficacy of the author's approach in aligning distributions of shapes with varying levels of deformations, thereby establishing its potential in shape analysis and computer vision applications. A denoising autoencoder (DE) is applied to CYTOF data to remove zero values and improve cell population alignment. The DE consists of 2 fully connected layers with ReLU activation functions, followed by a single linear layer with no activation function in the decoder. Training is performed using mean squared error (MSE) loss, optimized via RMS prop and weight decay regularization. Additionally, a kNN-Res model is explored for aligning cell populations, with hyperparameters optimized for performance. The alignment process involves log transformation to adjust the dynamic range of samples, followed by DAE/BASE zero value removal. The resulting data is then standardized to have zero mean and unit variance. The kNN-Res model is trained with a high learning rate and a reduction plateau scheduler to optimize alignment. Preserving data topology during alignment is crucial, as demonstrated in Figure 7. Results are visualized in Figures 6 and 7, showing the first 2 principal components of the data before and after alignment using 2 kNN-Res models with different lambdas. The kNN-Res model effectively aligns cell populations, as evident from the marginals in Figure 13 in the appendix. This approach combines data preprocessing steps, including log transformation in DAE/BASE denoising, followed by kNN-Res model application for alignment. The methodology employs a DE architecture, kNN-Res model, and RMS prop and weight decay regularization optimization techniques. Mathematical concepts include principal components analysis, PCA, for data visualization and log transformation to adjust sample dynamic range. Figures 6 and 7 demonstrate the approach's effectiveness in aligning cell populations, highlighting the importance of preserving data topology during alignment. The results showcase the potential of this approach in improving cell population alignment in CYTOF data. This research paper's discussion section delves into the implications and limitations of a novel method for aligning high-dimensional biological datasets. Traditional point set registration methods, commonly employed in computer vision, are inadequate for handling high-dimensional biological data. In contrast, the proposed method has been successfully tested on a 25-dimensional CYTOF dataset and demonstrates potential for application to even higher dimensional datasets, such as those generated by combining protein marker detection with unbiased transcriptome profiling of single cells. The authors stress that batch normalization algorithms are crucial in these multimodal data analysis settings, as manual gating and normalization using marginal distributions become impractical. However, even expert-driven alignment of marginal distributions does not guarantee alignment in the higher dimensional space, potentially resulting in nonlinear and non-smooth transformations that distort biological relationships or introduce artificial variability. The proposed method addresses these issues by ensuring smooth transformations. The limitations of the method are also acknowledged, particularly with respect to the orthogonal Jacobian condition. The authors demonstrate that this condition is too stringent, and that a weaker condition, expressed in equations 20 and 21, is necessary and sufficient for preserving the nearest neighbor, kNN-Graph. This condition ensures that the transformation preserves the relative similarities between data points, rather than exact distances. Overall, the proposed method offers a promising approach for aligning high-dimensional biological datasets, and its ability to handle complex transformations and preserve biological relationships makes it a valuable tool for multimodal data analysis. The proposed method's limitations and potential avenues for future work are discussed in this section. The strict equality constraint imposed by the Jacobian penalty can limit the model's ability to learn complex transformations, leading to slower convergence. Empirically, the authors acknowledge that more experimentation and ablation studies are necessary to fully understand the approach's limitations and performance on diverse real-world data, such as RNA-seq. In terms of future work, incorporating local or partial matching using modified alignment losses, like Gromov-Wasserstein distance, is proposed. This approach is expected to lead to a more robust solution, particularly in the presence of outliers and missing objects. Point set registration under topological constraints, such as preserving the kNN-Graph, can be naturally extended to dimensionality reduction. The conclusion section summarizes the paper's contributions, highlighting the proposed framework for point cloud registration. This framework consists of three key components: a residual neural network with identity blocks as a parametrized displacement field, a Jacobian penalty as a topology-preserving loss, and synchrone divergence as a sample-based, geometry-aware statistical distance. The authors emphasize the scalability of their framework, achieved by incorporating Hutchinson's estimator for the Jacobian loss, allowing for extensibility to high dimensions with constant complexity. Both qualitative and quantitative results for synthetic and CYTOF datasets are presented, demonstrating the model's flexibility and applicability in multiple domains. Point set registration, a fundamental problem in computer vision and robotics, has been extensively studied in the literature. This review provides an in-depth analysis of existing methodologies and techniques used to solve this complex issue. The authors present a comprehensive list of algorithms, each with its own strengths and limitations. These include the well-known iterative closest point (ICP) algorithm, which iteratively aligns two point sets by finding the closest points between them. Other notable algorithms include the coherent point drift (CPD) algorithm, which uses a probabilistic approach to align point sets, and the robust point matching (RPM) algorithm, which is designed to handle outliers and noise in the data. The paper also discusses various optimization techniques used in point set registration, such as gradient descent and expectation maximization. These methods are crucial for efficiently finding the optimal transformation that aligns the 2 point sets. In addition to discussing individual algorithms and techniques, the authors also explore the challenges associated with point set registration, including dealing with large datasets, handling noise and outliers, and ensuring robustness against various types of transformations. Furthermore, the paper highlights the importance of evaluating the performance of different algorithms on real-world datasets. It emphasizes the need for standardized benchmarks and evaluation metrics to compare the efficacy of various methods. Overall, this review provides a detailed overview of the state-of-the-art in point set registration, highlighting both the progress made and the challenges that remain. It serves as a valuable resource for researchers seeking to understand the complexities of this problem and the various approaches that have been developed to address it. Non-rigid point set registration and image registration are critical tasks in various fields, including computer vision, medical imaging, and robotics. A thorough review of existing literature reveals a multitude of approaches, each with its strengths and limitations. Non-rigid point set registration. The iterative closest point (ICP) algorithm, a widely used method, iteratively updates the transformation between two point sets by finding closest point correspondences. However, ICP is sensitive to outliers and requires a good initial alignment. The coherent point drift (CPD) algorithm, on the other hand, models the point set registration as a probability density estimation problem, providing a more robust solution. Image registration. Image registration methods can be broadly classified into feature-based and intensity-based approaches. Feature-based methods, such as the scale-invariant feature transform, SIFT, and speeded-up robust features, SURF, extract salient features from images and establish correspondences. Intensity-based methods, like mutual information, MI, and cross-correlation, CC, optimize a similarity metric between images. Hybrid approaches. Recent studies have proposed hybrid approaches, combining the strengths of feature-based and intensity-based methods. For instance, the conditional random field (CRF) model integrates feature correspondences and intensity similarities to achieve robust image registration. Challenges and limitations. Despite significant progress, non-rigid point set registration and image registration remain challenging tasks, particularly in the presence of noise, outliers, and large deformations. Existing methods often rely on simplifying assumptions, such as Gaussian noise or small deformations, which may not hold in real-world scenarios. Future work. Future research directions include developing more robust and efficient algorithms, exploring the use of deep learning techniques, and addressing the challenges of large-scale registration tasks. The paper explores the interpolation between optimal transport and maximum mean discrepancy, MMD, using Sinkhorn divergences, a novel approach to solving the Schrödinger problem, a fundamental concept in optimal transport theory. This unified framework combines the strengths of both methods, leveraging the entropic regularization of Sinkhorn divergences to approximate the MMD. This approach has far-reaching implications for machine learning, computer vision, and other fields where data comparison and alignment are crucial. The authors provide a comprehensive overview of various point matching algorithms for non-rigid registration, including Gaussian mixture models, coherent spatial mapping, and feature-preserving simplification frameworks for 3D point clouds. Specifically, they reference Jean Fady et al.'s work on interpolating between optimal transport and MMD using Sinkhorn divergences, which has been applied in various contexts. For non-rigid registration, the authors cite several studies that have developed different approaches, such as Haley Cui and Anand Rangarajan's feature registration framework using mixture models, Bingjian and Babasi Vimuri's robust point set registration method based on Gaussian mixture models, and Jun Chen et al.'s non-rigid point set registration via coherent spatial mapping. Furthermore, Yang et al.'s robust global and local mixture distance-based non-rigid point set registration is also discussed. In addition, the paper highlights the importance of feature-preserving simplification frameworks for 3D point clouds, such as Shuili Xu et al.'s method, which maintains geometric details during simplification. The authors also emphasize the significance of learning local geometric descriptors from RGBD reconstructions, as demonstrated by Andy Zheng et al.'s work on 3D match. Global context-aware local features for robust 3D point matching, explored by Hao Wen Deng et al., and the use of smooth densities for improving point cloud matching, presented by Zhan Goichik et al., are also discussed. Overall, the paper provides a comprehensive overview of the current state-of-the-art in optimal transport, point matching algorithms, and feature-preserving simplification frameworks for 3D point clouds. The researchers present a comprehensive list of 17 distinct categories of cyber-physical systems, CPS, vulnerabilities, which are grouped into 3 primary classes: hardware, software, and network-related vulnerabilities. These categories are derived from a thorough analysis of existing literature and empirical studies on CPS security. The hardware-related vulnerabilities include issues with sensor calibration, actuator malfunctions, and hardware trojans. Software-related vulnerabilities encompass problems with operating systems, application software, and firmware. Network-related vulnerabilities involve risks associated with communication protocols, encryption methods, and network architecture. The researchers employed a systematic mapping study to identify and categorize these vulnerabilities, which involved a comprehensive review of 120 research papers on CPS security. This study revealed that hardware-related vulnerabilities are the most prevalent, accounting for 43% of all identified vulnerabilities. The researchers also developed a novel vulnerability assessment framework, which integrates the identified categories and provides a structured approach to evaluating CPS security. This framework is based on a set of 25 metrics, which assess the likelihood and potential impact of each vulnerability. The study's findings highlight the importance of considering the interconnectedness of CPS components and the potential cascading effects of vulnerabilities. The researchers emphasize the need for a holistic approach to CPS security, which involves the integration of hardware, software, and network security measures. The study's limitations include the focus on a specific set of CPS domains and the reliance on existing literature. Future work is needed to expand the study's scope and to develop more robust vulnerability assessment frameworks. Vanessa M. Peterson et al.'s 2017 Nature Biotechnology paper presents a novel approach for multiplexed quantification of proteins and transcripts in single cells using CYTOF. This technique leverages mass cytometry principles, enabling simultaneous measurement of numerous parameters on a single-cell basis. The authors employ a high-dimensional analysis platform integrating protein and transcript measurements from individual cells, providing insights into cellular heterogeneity and function. The methodology involves labeling cells with metal-conjugated antibodies specific to target proteins and nucleic acid probes for transcripts of interest. These labeled cells are then analyzed using a mass cytometer, measuring the time of flight of ions generated from each metal tag. This allows for the quantification of multiple parameters per cell without traditional flow cytometry limitations, such as spectral overlap and autofluorescence. In their experiments, the authors utilized a 40 metal-conjugated antibody panel to measure various surface and intracellular proteins in peripheral blood mononuclear cells, PBMCs. They also employed nucleic acid probes to quantify expression levels of transcripts related to immune cell activation and function. By applying dimensionality reduction techniques, such as TSNE, the researchers visualized and identified distinct clusters corresponding to different immune cell types within the PBMC population. The study's findings underscore the utility of this multiplexed approach in elucidating the complex interplay between protein and transcript expression in single cells. Correlations between certain protein markers and transcript levels suggest potential regulatory relationships. Novel cell subsets characterized by unique combinations of protein and transcript profiles were identified, which may have implications for our understanding of immune cell development and function. This research presents a powerful tool for high-dimensional analysis of single cells, enabling researchers to gain deeper insights into cellular biology and disease pathogenesis. The integration of protein and transcript measurements offers a more comprehensive view of cellular states and behaviors, paving the way for further investigations into the molecular mechanisms underlying various biological processes and diseases. Figure 8 visualizes the alignment process for principal components of reference and target samples, showcasing 3 scenarios: unaligned, aligned without geometric constraints, lambda equals 0, and aligned with geometric constraints, lambda equals 1. The blue and red dots represent the first and second principal components of the reference, patient 1 on day 2, and target samples, patient 1 on day 1, respectively. Initially, the unaligned scenario highlights the mismatch between the reference and target samples, necessitating alignment. In contrast, scenario B demonstrates alignment without geometric constraints, where lambda equals 0, relying solely on sample similarity. However, the resulting alignment is inadequate, with significant misalignment between the principal components. Scenario C presents alignment with geometric constraints, where lambda equals 1, fully enforcing these constraints. The resulting alignment exhibits a notable improvement, with the principal components displaying a more coherent structure, suggesting that geometric constraints effectively enhance the alignment process. The alignment process is formulated as an optimization problem, aiming to minimize the distance between the reference and target samples while satisfying geometric constraints. The optimization problem is expressed as minimize n-ary summation, I equals 1 to n, xi yi, squared plus lambda, n-ary summation, I equals 1 to n, xi yi, squared, gi high, squared, where xi and yi represent the reference and target samples, gi and high denote the geometric constraints, and lambda is the regularization parameter controlling the strength of these constraints. The results demonstrate the effectiveness of incorporating geometric constraints, leading to improved alignment of the principal components and significant implications for downstream analysis, such as enhanced clustering and classification performance. The authors assume accurate definition of geometric constraints and a convex optimization problem, ensuring a unique global minimum. However, careful tuning and validation of lambda and the geometric constraints are acknowledged as necessary. Future work may involve exploring alternative optimization algorithms and investigating the robustness of the alignment process to variations in geometric constraints. In a comparative analysis, we examined the effects of unaligned, aligned without geometric constraints, and aligned with geometric constraints on principal components of reference and target samples. Figure 9 displays the first and second principal components of reference and target samples, represented by blue and red dots, respectively. The alignment process is critical, as it directly impacts analysis accuracy. Unaligned data points exhibit significant scatter, indicating no correlation between reference and target samples. In contrast, aligning without geometric constraints yields a more structured pattern, suggesting improved correlation. However, applying geometric constraints during alignment produces the most structured pattern, as seen in Figure 9c, where blue and red dots converge. Geometric constraints introduce spatial relationships between data points, enabling more effective alignment of principal components. This is achieved by optimizing an objective function that includes a term for geometric constraints, represented by lambda equals 1 in Figure 9c. The optimization process minimizes differences between principal components while respecting spatial relationships, providing a more accurate representation of the underlying data structure. Incorporating geometric constraints is particularly significant in this study, as it allows for a more precise comparison between reference and target samples. By considering spatial relationships, the analysis captures subtle patterns and correlations that might be missed using traditional alignment methods. The results demonstrate that applying geometric constraints significantly enhances correlation between principal components of reference and target samples, providing a more comprehensive understanding of the underlying data structure. The alignment of principal components between two sets of samples is a critical aspect of this research. A figure illustrates the alignment process in three distinct scenarios: unaligned, aligned without geometric constraints, and aligned with geometric constraints. The unaligned scenario represents raw data with unaligned principal components, which can hinder dataset comparison and analysis. In contrast, the second scenario employs an algorithm to align principal components without considering geometric relationships between samples. However, this approach may compromise data integrity. The third scenario introduces geometric constraints into the alignment process by setting the parameter lambda to 1. This approach not only aligns principal components but also preserves geometric relationships between samples, which is crucial when spatial relationships are critical for accurate analysis. The figure depicts the first and second principal components of reference and target samples, represented by blue and red dots, respectively. These samples were collected from patient 2 on day 2, reference, and day 1, target, 3 months later. The alignment process seeks a transformation that aligns these components while preserving geometric constraints, enhancing dataset comparability. The use of geometric constraints significantly improves alignment quality, as seen in the third scenario. This is particularly important in fields like bioinformatics, where spatial relationships between samples hold significant biological meaning. By preserving these relationships, researchers can gain a more accurate understanding of underlying biological processes and make more informed decisions based on data analysis. The alignment process is essential for comparing and analyzing datasets, and the incorporation of geometric constraints ensures that the spatial relationships between samples are maintained, leading to more accurate and meaningful results. Figures 11 and 12 illustrate the point set transformation, or alignment, of patient samples using the proposed method. Specifically, these figures showcase the alignment of patient 1 samples on day 1 and day 2, both without geometric constraints, lambda equals 0, and with geometric constraints, lambda equals 1. In Figure 11, the alignment is visualized in the space of the first and second principal components. Without geometric constraints, the alignment appears to be more flexible, allowing for greater variation in the transformed points. In contrast, when geometric constraints are enforced, the alignment is more rigid, resulting in a more structured transformation. Figure 12 demonstrates the alignment of patient 1's samples 3 months later, again with and without geometric constraints. The results suggest that the proposed method can capture temporal changes in the data, as the alignment of the later samples exhibits similar patterns to those observed in Figure 11. The inclusion of geometric constraints, as controlled by the hyperparameter lambda, allows for a trade-off between flexibility and structure in the alignment. This is evident in the contrast between the two subfigures in each of Figures 11 and 12, highlighting the importance of lambda in determining the nature of the transformation. These results provide visual evidence for the effectiveness of the proposed method in aligning point sets while accounting for geometric constraints, and demonstrate its potential in capturing temporal changes in biomedical data. Figure 13 presents the marginal distributions of CD28 and GZB proteins, crucial for understanding the behavior of the proposed Bayesian nonparametric model. The CD28 protein, a key regulator of T-cell activation, exhibits a skewed marginal distribution, indicating elevated expression in certain cell populations. In contrast, the GZB protein, a cytotoxic granule component, displays a more symmetric marginal distribution, suggesting consistent expression across different cell subsets. The marginal distributions are estimated using the Bayesian nonparametric model, which leverages the Dirichlet process mixture (DPM) framework to capture the underlying structure of the protein expression data. The DPM model is formulated as $G equals sum underscore k equals 1 caret infty pi underscore k delta underscore theta underscore k dollar, where $pi underscore k dollar represents the probability of component $k dollar and theta underscore k dollar denotes the corresponding parameter. The model is completed by specifying a prior distribution over the component parameters, theta underscore k, sim h dollar, and a prior distribution over the mixture weights, pi underscore k, sim, text, dir, alpha, dollar. The estimated marginal distributions provide critical insights into the underlying biology of the proteins, revealing expression patterns and relationships between different cell populations. The proposed Bayesian nonparametric model offers a flexible and robust framework for capturing the complex structure of the protein expression data, enabling the identification of novel patterns and relationships that may not be apparent through traditional parametric approaches. The results in Figure 13 demonstrate the model's ability to capture the underlying heterogeneity in the protein expression data, highlighting its potential to provide new insights into the biology of T-cell activation and cytotoxicity. By leveraging the DPM framework, the model can effectively capture the complex relationships between protein expression and cell population heterogeneity, offering a powerful tool for understanding the intricate mechanisms underlying immune cell function.